Nothing really to talk about with those. They're just, it's a positive ion and a negative ion. Positive and negative attracts. That's it. They stick together. Covalent is a little bit different because we're not using metals, we're not using ions, we're not using charges. So what's holding these things together? And what's holding them together is called covalent bonds. And it works like this. So if we go back to our hydrogen atom, how many valence electrons does hydrogen have? One, just one, in a neutral atom. So let's draw it on the atom like that. All right, so there's hydrogen with its one electron. How many electrons does it need to have a full shell? Two, so one more, right? So two total. So we talked about in ions, we would say, all right, well, it can gain an electron and become H minus, or it can lose an electron and become H plus. And both of those ions exist. That's fine. But there's another way that it can get those two electrons in its shell, and that's by sharing with another atom. So if another atom of hydrogen gets close enough, and it also has one electron, then those two electrons actually occupy both valences at the same time. So you've got two electrons occupying both valences at the same time. There's various ways to draw this. So we could draw it like this. And if we look at each of those atoms, we can actually count those two electrons for each valence. So we would say the hydrogen on the left now has two valence electrons. The hydrogen on the right now has two valence electrons. So both valences are filled in that case. And that makes that interaction particularly stable. It's a stabilization. And this happens purely from that physical interaction. So the two hydrogens have to be close enough to each other that those electrons actually are in both valences at the same time. So the valence shells overlap. And that's where that word covalent comes from. The valence shells overlap and the electrons are in both at the same time. If those atoms were to move farther apart from each other, they could no longer do this. And so they'd no longer have that stabilization. So most of the time when we draw this, we use this line to represent that. But it's important to remember that that line means the exact same thing. So that line specifically means a covalent bond, which is two shared electrons. So we only use lines in that context. So we would not put a line between, let's say, Na and Cl in NaCl, because that's an ionic compound that's not covalent. So that's not a covalent bond. So even though it seems like the line just means kind of connected together, it actually has a specific chemical meaning about what's going on. All right, so that's a covalent bond. Good with that so far? Okay. Let's move on to a larger atom and see how it works with something else. So let's look at oxygen. How many valence electrons does oxygen have? 6, yeah. So we can look at the periodic table. It's in 6A, 6 valence electrons. And how many does it want to be full? 2 more, so 8 total, right? So there's the 6, and sometimes we can draw it like this so that we can see easily that it's missing 2. So if we could fill in this spot here and this spot here, then we'd have a full valence shell. So just like before, we talked about you can add 2 electrons and make it O2 minus, and that fills the shell. But like with hydrogen, there's another way to do that too. Rather than transfer electrons, other atoms can just get close enough so that the electrons occupy both valences at the same time. And so that can happen with another oxygen atom, or it could happen with something like hydrogen. So we could take a hydrogen atom here and another one over here and share those together. And now we can say that oxygen has its 8 valence electrons that it wants. And each of those hydrogen atoms has the 2 electrons that they want. So it works out for everybody. In line form, that would look something like this. For now, the angles don't really matter. We'll get into that another time. And this oxygen would actually have 4 valence electrons, 2 pairs, that are not involved in the bonding. So they're just kind of hanging out there. They're not part of the bonding, and that's fine. Sometimes we draw them there, sometimes we don't. They do some stuff sometimes, but that expresses then all of the electrons. So if we look at a compound like this that has the lines, we can still do our accounting and make sure that all the valences are filled. So we can say, all right, this oxygen has 2, 4, 6, 8 electrons around it. This hydrogen has 8 from these, or has 2 from these 2. This hydrogen has 2 from this bond. So in that way, all the valences are filled. You can look at the bonds and the leftover electrons in a compound and figure out if the valences are filled or not. So let's see what happens when oxygen binds with itself. So same thing. We're going to start with this oxygen with 6 electrons. Another oxygen with 6 electrons. So we're going to do the same kind of thing that we did with hydrogen. We can connect those together. To make something like this, and then we want to ask, is that correct? Is that a good structure for the dioxygen molecule?
No, because the bottom here.
Yeah. Right. So if we go back and actually check this, we can say, okay, well, this oxygen has 2, 4, 6, 7. That's not 8. So that's not right. So that doesn't work. So the solution here, we can't add more electrons because they have the electrons that they have. But we can always rearrange the electrons and put them in different places and share more. So in this case, we could share these electrons also. And we call that a double bond. And that one's going to consist of 4 shared electrons. So again, 2 per line. So going back up to this definition, if a covalent bond is 2 shared electrons, then the double bond, we have to show 2 lines to show 4 shared electrons. And now everything works, because if we look at each of those oxygen atoms, this one has 2, 4, 6, 8 electrons. And this one has 2, 4, 6, 8 electrons. So all the electrons from the bonds count in both atoms that they're connected to. All right, so now you try one. Actually, try 2 of them. Try drawing a structure like that for Cl2, so ClCl, and N2. And remember that your ultimate structure should show the connections, but each atom should have enough electrons to fill its valence. There should be 8 electrons in the valence for each atom when you're done. All right, did you get it to work? Maybe, maybe not. Remember, you can always check if it works or not by counting up the electrons. In this case, both chlorine and nitrogen want 8 electrons. So in your finished structure, there should be 8 electrons around each atom, including the bonded ones for each. So let's try that together. For chlorine, how many valence electrons do we start with?
7.
7, right. So that means we need one more. So in that way, it's going to be very similar to hydrogen, the way that it interacts with other things. So we can draw another chlorine. And share those, and now each has 8. So we could draw this dot style like this. Or we could draw it line style like this. In chlorine's case, it can't take any multiple bonds. It doesn't need them, first of all, but also it can't take them because that would give it more than 8 electrons. So let's say you decided to share more just because you wanted to try it out. Like that. So let's say we also shared these two. I made a double bond. So we can count this out and see why it doesn't work. Remember that for each chlorine, we have to count all the electrons, including the ones in the bond. So that makes 2, 4, 5, 7, 9 electrons, since each bond has 2. That's 9 electrons, that's 9 electrons. So that doesn't work. Gotta have 8 electrons. So we can always check to make sure that we have the right number. All right, on to nitrogen then. Nitrogen is going to start with 5 valence electrons, right? So if we have 2 of those, again, we can start by saying, all right, if we shared those, then each one would have 2, 4, 6. That's not quite enough yet. So let's also share these like oxygen. Now each one has 2, 4, 6, 7. Almost there, so what do? Yeah, you got to share another pair. So let's share those 2 also. It's starting to look a little bit messy, but if we kind of put them all back in the center, what we're really doing here is sharing 6 total electrons, so 3 pairs. And now it works. Each atom has 8. See that? See all 8 for each atom? So you draw 3 lines, right? Each shared pair gets a line. So if you got to share 3 pairs, you need 3 lines. That's what that one. I'm good so far? Okay. So that's a covalent bond. Now you've noticed all the ones that we've looked at here have the same one. Yeah. The number of, oh, so the total number matters because that's the valence electrons. Where you put them doesn't matter. So like we could have gone 1, 2, 3, 4, 5, like that, right? Like, is that what you're asking? Yeah. So that doesn't really matter. What matters is that you figure out how many need to be shared. And then I just kind of drew them in a way that made drawing these circles around them more convenient, but it doesn't really matter. As long as you can still figure out how many need to be shared overall, that's what matters. In fact, drawing all the dots in the individual atoms doesn't really matter at all. What we want is to be able to do this, to be able to ultimately draw a structure that has the appropriate number of bonds and electrons and things. So however you get to that point is fine. Yeah, good question. Thanks. Okay, so let's look at something that happens in these bonds when there are two different atoms connecting together. So if we go back to our example of hydrogen, because that's a small, nice, simple example. There are two shared electrons. The electrons are shared in the hydrogen valences. And they are actually shared evenly, which means that if we kind of look around this molecule, we would see that the electrons are shared evenly between the two hydrogens. So you have this symmetric molecule. Sometimes the electrons are more in one valence or more in the other, but overall, on average, they're symmetric and they're shared evenly. When the two atoms are not the same, the electrons are often not shared evenly. So for example, if we looked at HCl, actually, I'm going to get rid of, even though there are extra electrons there, I'm not going to show them here because I don't want it to confuse the issue. If we look at where the electrons are in that same two-electron bond between H and Cl, instead of being shared evenly, they're actually pulled more toward the chlorine. Save my. Electrons are pulled more toward the chlorine here in this example. And what that does is it changes the electrical structure of that molecule because electrons are charged. What's the what charge are they? They're negative. So if the electrons are more on one side than the other, that means that this molecule is going to have a negative side and a positive side, which would not exist in hydrogen. So in this one, this side would end up being kind of more negative. And because the electrons are missing from the hydrogen side a little bit, this side would end up being more positive. So we would say that this molecule has two poles, a positive pole and a negative pole, or a positive side and a negative side. And the word we use for that overall is polar. So we would say that this is a polar bond because it has a negative side and a positive side. Yeah.
Can you just say that bonds with positive and negative?
Yes. So in an ionic bond, there is a positive ion and a negative ion, and they connect together. In a polar covalent bond, it is not that extreme. That's really the difference. So the electrons are still shared between the two. They just kind of spend more time on one side than the other. So, so rather than being fully transferred like in an ionic compound where the electrons were all extra ones are on this one and all the missing ones are here, they're actually just partially shared. And actually there's special symbols we use to show that. So in a polar bond, if we want to show that, that difference, rather than using plus and minus, which would indicate ions, which is a source of some of that confusion, instead we use the Greek letter delta, and we say it's delta minus on the chlorine and delta plus on the hydrogen. And that stands for a partial charge instead of a full charge. So rather than being a fully charged chloride ion, it's just a little bit of a charge, a partial charge on the Cl. So partial negative on the Cl, partial positive on the H. And so that's a polar covalent bond. One of the things we want to be able to do is determine whether a bond will be polar or not. So to do that, we have to know some numbers, or we have to look up some numbers called electronegativity. Electronegativity is the ability of an atom to attract electrons in a covalent bond. So it's not just like attracting electrons from the atmosphere or whatever. When it's bonded, if something has a high electronegativity, that means that it's going to do that thing where it pulls the electrons more toward it, leaving a more negative side and a more positive side. So you can look this stuff up in a table. There's one in the book. Oops, I forgot to log into Blackboard, so I'll do that. Take a look at the book here. Okay, it's over in section 1, V1. So it looks like this when it's superimposed over the periodic table. Oh, I'm going to copy this into the notes. I know it's probably a little small. If you've got a book, you can look at it, but you don't need to know all the numbers. Most of the time, the numbers are kind of irrelevant for us. But what happened to that extra table? You can do okay there? No, okay. There was a table in here, wasn't there?
No.
I thought we pulled in a table one day. Anyway, you can jump in with somebody. So anyway, you don't need to know all these numbers because we're not going to deal with covalent bonds with metals much anyway. And so pretty much everything over on the left doesn't matter too much. What is really important is these green ones that have the highest electronegativities. So it is worth knowing those because that's where we're mostly going to find this effect, this polarity effect. When one of those atoms is bonded to something else, we tend to get a pretty significant difference in electronegativity that then leads to this polarity. So we can say, in general, electronegativity greater than 0.4, so 0.5 or above. Whoops, sorry, difference in electronegativity. So in general, the difference in electronegativity of more than 0.4 indicates a polar bond. So if we want to figure that out, we could take something like HCl and say, I don't know, is it going to be lopsided? Is it going to be polar or not? So we look up H, which is 2.1. We look up Cl, which is 3.0. The difference is 0.9. So we would say that that one is polar. If we're looking at what? The difference in the two electronegativities. So H is 2.1 and Cl is 3. 3 minus 2.1 equals 0.9. See that?
Yeah.
Okay. So if we look at like a HC bond, which is a really common bond, we'll get into that more when we talk about organic chemistry and biological molecules. But a CH bond or HC bond, we've got 2.1 for H, 2.5 for C. So that difference is 0.4. So we would probably call this one nonpolar and say that there is really not much of a difference between the two. So we would not expect the electrons to be more toward one than the other. If we look at something like water, water is made up of OH bonds. So what's the difference in electronegativity between O and H? Let's see. Yeah, it's 1.4, so pretty significant. So that one's very polar, and in a couple chapters we'll see why that has some pretty major effects. And then also, if we wanted to write the partial charges on here, where would the partial negative charge go? On the oxygen or the hydrogen? Because the electronegativities can also tell us that. So which of the two atoms is pulling harder?
Oxygen.
The oxygen. So the electrons are getting pulled toward the oxygen, and that makes the oxygen partially negative and the hydrogen partially positive. So whichever atom is getting more electrons is becoming more negative, and whichever is being pulled away from is becoming more positive. All right, does that make sense? Okay. All right, so that's polarity. We're going to take a break from polarity. Sorry, not in class. We just started. Come on. Yeah.
Will we get a periodic table like this for this?
I'm not sure, but if not, you won't have to do the comparing the numbers. So
See, that's what I was.
yes, so these are different values. These are the electronegativity values, and that's not on that table. So let's talk about what happens if you need to know whether a bond is polar and you don't have access to this table. In some cases, you're just kind of screwed, like you can't figure it out. Because if it's some unusual atoms or something, or you're not really sure, it could be impossible to figure that out if you aren't looking at the table. But there are some shortcuts. For instance, knowing that NOF and Cl are the highest ones can really help you out because the difference, like O and F particularly, 3.5 and 4, the difference between those two and everything else exceeds that 0.4 threshold. So anything that's not at O or F, that's bonded to O or F, that bond will always be polar. So everybody see that? There's nothing you can bond to O or F that would put you in the nonpolar range except for themselves. So an OO bond is still nonpolar because there's no difference. So that's a big clue right there. And then with N and Cl, it's a pretty good chance that whatever's bound to them is also going to be polar. Right? Because I think there's just a couple exceptions. Anything that's 2.5, which is just C and S, would just barely make it. But even that would still be polar. So really, if you just know those four green ones, I guess Br is 2.8. But everything besides that, if you know those three green ones, anything bound to those is going to be polar. All right, so unless, and I wouldn't ask you like to determine if a PS bond was polar or something unless I gave you the numbers. So you should know that the most polar ones are up in the corner, and that should allow you to answer most of the questions that you have about whether or not something is polar. Okay, so I was saying we're going to take a break from polarity and stuff for a little bit until the chapter after next, when we start talking about the intermolecular forces and how molecules attract each other. Because what ends up happening is this idea gets applied to whole molecules, and then we can figure out whether molecules will attract each other or not based on this. Okay. Any questions more about bonding or electronegativity? All right, let's move on to equations. All right, a chemical equation is a description of a chemical reaction that we can put down on paper. So here's one. That is a chemical equation. Can anybody describe what that's telling us happening? Yeah, so there's a chemical reaction happening, and there's some reactants and products. So we can start with that. The things on the left that we're starting with, we're going to call the reactants. So to the left of that arrow. Then we show this arrow, meaning that these things are becoming this other thing. And whatever's on the right, we call the products. In this case, there is just one product. What else can we say about this reaction? What is happening here? Yeah, it's a chemical reaction.
Gas changing into.
How do you know gas changing into liquid? That's a good point, because how do we know what kind of states these things are in? Any ideas? Yeah, if you've seen this sort of thing before, these little letters in parentheses, those tell us the state of each compound. There's 4 common abbreviations that we use for the state. So we've got G for gas, L for liquid. It's not, it's water vapor. So the fact that there's a G tells us that it's not liquid water, it's water vapor. L for liquid, S for solid. And then there's a 4th one that we'll see a lot, AQ. AQ stands for aqueous, which means dissolved in water. So if you saw, all right?
Yeah.
Okay, good. If you saw NaCl with a little s, oh, we're out of chairs though. Here, you can take one. Sorry. To get that other table in here. Thursday. All right, so NaClS means like salt crystals, right? Solid sodium chloride. NaCl AQ means salt water. where the ions are broken up into water. So that little thing can make a big difference if you're planning out a reaction or something and you are wanting to know what form of the reagent to use. In a lot of cases, solid reagents don't react. Like if you wanted to react chloride ions with something like we did last week with the silver, solid sodium chloride, those chloride ions are all tied up in there. They're not really going to react. But if you dissolve it in water, then they can kind of move around and react and do stuff. So that's why we see that AQ a lot. All right, so that tells us that something about the state. So this tells us hydrogen gas and oxygen gas are combining to form water vapor. And that's the information that we get from this equation. Does anybody see any problems with this equation as I've written it here? I'll give you a hint. There is one problem. Yeah, there's some oxygen missing. So if we look at this down at a molecular level, we know that H2 looks like this. We know that O2 looks like this. And we know that H2O looks like this. And there's something missing there. You see that? So I've shown 2 hydrogen atoms that are connected. 2 oxygen atoms are connected. They break apart. They recombine into water. And then one of the oxygen atoms disappears. And that's not okay. The reason it's not okay is because matter doesn't just disappear. It doesn't just appear either. There's something called the law of conservation of matter that says that in a chemical reaction, you can't just make matter vanish or appear. It has to actually all be conserved. All the atoms can do in a chemical reaction is rearrange themselves. They can't just cease to exist. So the way we've written this equation then is not quite right because we've shown an oxygen atom simply ceasing to exist, and we don't have that kind of power. So that's a problem. So what do we do instead? Any ideas on how we would fix that? What? Just add a 2. Yeah, let's add a 2. So if we move this over so we have a little room here. So if I put a 2 there, is that good? Depends on what we mean by good. Some people are shaking their head. Why is that not okay? Yeah.
To the other side too.
Well, you tell me. Is there something changing here? Yeah, that's the bigger problem. So H2O2 is a different compound. Does anybody know what it is? It's hydrogen peroxide. Is that the same as water? No. So don't drink it. Hydrogen peroxide is not the same as water. So we can't do that. Because what we just did is made an equation for a totally different reaction. Because remember that the point of this is that you're writing down something that symbolizes an actual physical process. So you can react hydrogen and oxygen gas together. I would do it, but it blows up and get in trouble. So we're not going to do that, but you could do it, and you'd find that only water comes out. Hydrogen peroxide does not come out of this reaction. So this is wrong. Here. Not quite, but it's actually would be combination or composition because you're putting things together. Let me move this back over so it fits better. There we go. So we can't change the subscripts. You can never change the subscripts because that gives you different chemical compounds. And if you want a different chemical compound, fine. But if you're thinking about that this equation is not balanced, something's out of balance, you can't change the subscript. So equations need to be balanced. And our first note on that is don't change the subscripts. You can't change the little numbers. And it's so tempting because if you change the little numbers, it's usually way easier. You can usually just make like 1 or 2 little changes and you're done. But that doesn't work. That's a totally different process that you're talking about. So what we really want to do to change this is change the ratio by which the reactants react with each other and the products are formed. So in other words, the way that I wrote it initially, saying that one molecule of H2 reacts with one molecule of O2 to make one molecule of water, that's the thing that's wrong. It's not a 1-to-1-to-1 ratio. And if we change the ratio, we can get it to work out without losing any atoms. Does anybody see how we could change the ratio and not lose any atoms? But
You can add coefficients.
yeah, what does that mean?
You add the amount of each.
Yeah, we change the number of each molecule that we're reacting. So does anybody see what numbers of the different reactants we could use and make this work? Yeah. Right. So if we use 2 molecules of hydrogen instead of just 1, then we would make 2 molecules of water instead of just 1. And if you look at those now, that works because we start with 4 atoms of hydrogen and we end with 4 atoms of hydrogen. We start with 2 atoms of oxygen and we end with 2 atoms of oxygen. Does everybody see how it works now on those little pictures? The atoms are no longer disappearing. The way we express that in the equation is by putting numbers out in front of each compound, which we call coefficients. So we can put a 2 here and a 2 here. And that tells us that now we're talking about 2 molecules of hydrogen reacting with 1 molecule of oxygen and making 2 molecules of water. And now all the atoms are fine. We're rearranging them, but we're not getting rid of any of them. Yeah.
Oh, never mind.
Okay. So that works for this, and you may have been able to see that. Maybe not, that's fine. Just by looking at this equation, because it's kind of a simpler one. But as these equations get more complex, it's hard to just kind of look at it and figure out what numbers need to be there. So it's better if we can figure out a way to do it systematically, like step by step, to find those numbers. So let's try that. So here's an equation for the combustion of propane gas, burning propane gas. So when you burn propane gas in enough oxygen, you make carbon dioxide and water. And you'll get to do a little bit of combustion today, I think. All right. So the first step in balancing an equation is always figure out if the equation is balanced to start with. So to do that, you want to count the number of each type of atom on each side of the equation. So I would go, all right, on this side, we've got 3 carbons. We've got 8 hydrogens. We've got 2 oxygens. Everybody see where I get those numbers from? We're going to do the same thing on the other side, counting just the products. 1 carbon, 2 hydrogens, 3 oxygens. Now, we have to count everything on the whole side. So we've got 2 oxygens from the CO2 and 1 from the H2O. We put those all together in our total to make 3 oxygens. All right. So we can see from those numbers pretty clearly that this is not balanced, right? So let's start balancing it. To balance it, what we're going to do is change some coefficients, change those numbers out in front, try to bring the atoms into balance one at a time, one type at a time, and then we're going to continually recorrect our totals as we change things. So which one do you want to try to even out first? Any preferences? Hydrogen? Sure. So how would we make the hydrogens even? Does anybody see how we could do that?
4.
Yeah, we could add a 4 in front of the H2O because if we have 4 water molecules, that gives us 8 total hydrogens. And then the other thing to always remember is whenever you change a coefficient, make sure you update the totals for every atom, not just the one that you're working on. So now we balance the H's, but we also changed our count of oxygen in doing that when we put that 4 in there. So now instead of 3 oxygens, we have 6, right? Yeah. 6, yeah. 2 from the CO2 and 4 from the 4 waters. All right. So now let's work on the carbons. How do we balance the carbons? What number are we going to put in front of the CO2? A 3, right? So that changes this to 3. And now we change our total oxygen count to 10. Everybody see the 10? 3 times 2, so that's 6 for the CO2. And then an additional 4 from the 4 water molecules. Makes 10 overall. So we're almost there. We've got the same number of carbon atoms on each side, same number of hydrogen atoms on each side. And now all we have to do is balance the oxygen atoms. So what number can we put in front of the O2 to get 10 total? 5. And now we double check our numbers, make sure everything works out. And it looks like, yes, this is balanced. It's all good. All right, so see how that works? Kind of keep changing things until you get them to balance out. Okay, let's try another one. So I want to do a pretty similar one. Another combustion, but this time butane instead of propane, C4H10. And this time you try it. See if you can do the same thing and come up with numbers to balance that.
Matter what side you start on?
No, it doesn't matter what side you start on. Did anybody run into some trouble with this one? What kind of trouble? Oxygen trouble? It's never a good kind of trouble to have. Yeah, let's talk about that. I'm gonna set up the totals here, and then we'll go through it. Keep working on it if you're still working on it. See if you can come up with a solution with your oxygen trouble. Try breathing deeply or something. So is this where you get stuck? Yeah, because you've got 13 oxygen on the right. Everything else is balanced, but there's 13 oxygen on the right. And you can only change the left in multiples of 2. So you can put a 6 there and get 12. You can put a 7 there and get 14. But you can't put a 6.5 there and get 13. So what do you do? Yeah, double everything. So if you run into this problem, which actually kind of comes up a lot, one way you can change it is just by doubling everything else, because that's going to get rid of your odd-even problem, because any doubled odd number is always going to be an even number. So let me show you how that works. You put a 2 here instead of a 1. And then any numbers that you've already filled in, you just double. The reason that works is because we haven't changed the ratios of those. So that's going to give us 8 carbons and 20 hydrogens on both sides. Just because we know we're going to have to change that number anyway. So going from 1 to 2 isn't going to help. You can, it's not going to hurt anything. So now we see 26 oxygen on the right. That's a nice even number. So now we can put a 13 in front of the oxygen to get 26 on the left also. And now everything's balanced. So that is something that comes up now and then. Which one?
13.
Because 13 times 2 is 26. And so that would give us 26 total oxygens on this side and 26 on this side. So we wanted to know what number can we put here to get 26 on this side. All right, we're going to take it one more step. Maybe. Grab this one from the book here. Access denied. Okay. Maybe I won't be taking this one from the book. So here's an example from the book. Maybe. No, that's small. I'm going to try to make it bigger here. Can everybody read that? Balance the following equation. Aqueous ammonium sulfate reacts with aqueous lead nitrate to produce aqueous ammonium nitrate and solid lead sulfate. This one gets a little bit trickier because you're not given the formulas. But you should be able to construct formulas from all those names. So give it a try. We need a periodic table to help you out. If you want to check back on your list of polyatomic ions, you can do that also, but keep in mind that you'll need to know those for the quiz on Thursday and the exam next week. Yes, all of these chapter objectives. So I'll tell you where we stop.
Yes.
Is the exam on the paper or is it like
On the paper, on paper. Yeah.
Is the practice quiz coming up or no?
No, I wasn't planning on having a practice quiz for this one because we already did one. Because it'll be the same format, just with different questions this time.
So like on the pluses and minuses important.
They- Yeah, only in that you need to know how many of each ion are in the formula. Otherwise, you're not going to have the right number of each thing.
You have to balance ammonium and sulfate first.
Mm-hmm. So you have to get a neutral compound for that first, and then you can put them all into the reaction. No, that's a good question. Yeah, so there's some information missing here. Sorry. It should be lead 2 sulfate. All right, in the interest of time, because we only got about 5 minutes left, good job with this. Good job struggling with it. I know it's tough to try to put all these compounds together and then also put them in an equation and balance the equation. So let me show you what the equation looks like so we can focus on the balancing. So ammonium sulfate is NH4 because ammonium is +1, sulfate's -2, so you need 2 ammoniums to balance out that compound. That's aqueous. Lead nitrate, this should also be lead 2 nitrate. So if it's lead 2, that's lead +2. Nitrate is -1. So you need 2 of the -1 nitrates to offset the +2 lead. Also aqueous. And then our products are aqueous ammonium nitrate. And solid lead sulfate, lead 2 sulfate, which is PbSO4. Because sulfate is -2, lead is +2, so you just need 1 of each.
It's a matter of like.
Yes, well, yeah, it does. We always put the cation first, so cation. All right, so we have a couple issues here beyond just putting the compounds together, but one thing you probably noticed is if you don't put the compounds together exactly right, it throws off the whole balance of the whole equation because all your balancing numbers are going to be different. So for instance, if you made ammonium sulfate NH4SO4 instead of NH4 then you're not going to get the coefficients right because everything depends on everything else to balance properly. So that's why we spent a good bit of time working on putting those compounds together from the names. Those need to be there and they need to be right before you can even start to balance the equation properly. So keep working on that. The other thing you might notice is in balancing this equation, you notice that ammonium contains N, but nitrate also contains N. And then every single compound in the formula, in the equation, contains oxygen. So when you change those, it's going to kind of keep throwing everything else off, and that can get a little bit tricky too. So one way that you can help that, one way that you can balance this more easily, is recognizing that the polyatomic ions stay together throughout the equation. In other words, the sulfate on the left stays sulfate on the right. It just changes what it's paired with. So that can be helpful in balancing because we can balance them as whole ions. So we can say on this side we have 2 ammoniums and we have 1 sulfate and 1 lead and 2 nitrates. Rather than saying we have 4 N's and 10 O's, which could get a little bit confusing. It'll still work if you do it that way. It just might take a little longer to balance. And then on this side, 1 NH4, 1 SO4, 1 lead, and 1 nitrate. So when you see these whole ions and the ions are staying together, the polyatomic ions are staying together throughout the equation, then you can keep them together for the balancing. So in this case, to balance it, all we have to do, I think, is put a 2 here. That changes the ammonium, that changes the nitrate, and everything's balanced. So probably the hardest part of this is putting those compounds together properly in the first place, right? All right. Let me give you one more to try on your own, although we're running out of time. So we'll start with this one next time, or we can talk about it in lab if you want. So go ahead and write that one down. We don't really have time to go through it right now because it's the end of class. I will put up a place to put in your free labs right now, and so you can submit those at any point, and we'll start up at 2 with lab. So, does everybody have this? Can I get down? Okay. All right, I'll see you in about 15 minutes.